Hello, welcome to another video. So today we are going to talk about replication. So in any distributed system, replication is the backbone of building a reliable system, and that will be easily scalable, especially in the fault tolerance area. So let's discuss about it. So let's try to understand the motivation first. Why do we need to replicate the data? So of course, replication is creating and maintaining multiple identical copies of data across different nodes or locations. So why do we need to replicate data? Why do we need to maintain copies of the same data across multiple machines? Well, we need high availability. So systems remain operational even if a node fails. So let's say I have databases in machine 1 and I have another copy of the same data in machine 2. So in case the machine 2 goes down, machine 1 is still available and the users can still access it. So this is the concept of high availability, where even though the system partly fails, the other bits of the system keep on working as expected. Fault tolerance, protection against data loss and system crashes. Of course, like along the similar line, if the system crashes, if the database is itself corrupt and it can't recover, still we are safe because we have another copy of data. And maybe later, if we spin up another new copy of the system, we can just replicate this data again. So we are protected from data loss even if there is some disaster in one particular location. Then scalability. Of course, this is a big part in distributed systems. If we have a lot of users accessing our data, then we need to distribute the read loads evenly, as much evenly as possible. So if we have copies of the same data based on the region of the user, we can distribute the load. So let's say, for example, this machine 1 is in USA and machine 2 is in UK. So a user in USA, they can directly connect to the database of USA, whereas a user in UK can directly connect to the database in UK. So in that case, the load is also distributed because USA database does not become a single point of failure, and also because UK user is closer geographically to the UK data center, the request is much faster. So it's a win-win scenario. Disaster recovery, yeah, I briefly talked about this before. In case M1, M2, one of them goes down due to some natural disaster, we can recover the data again. And performance, reduce latency by serving data from closer replicas that we talked about in the USA UK example. Let's move on. So let's briefly talk about how the replication topologies look like. There are mainly three types of replication strategies we follow. The first one is leader follower, second one is multi-leader, and third one is leaderless or peer-to-peer. So let's talk about each of them now. Leader follower, this is the most commonly used model. So this is something where we have multiple copies of the same DB. So let's say I have a leader and then I have two followers. And what it does is, whenever there is a read request, that can be served by any of the replicas. But whenever there is a write request, it can only be served by the leader, and that leader then takes care of replicating the write to the followers. So what are the common examples? Well, MySQL, PostgreSQL, these are the databases that follow this architecture, this leader follower architecture. Also, MongoDB is another example that comes to my mind that follows this leader follower architecture. Okay. Now let's talk about the multi-leader model. So in this case, there can be multiple leaders, and let's say there are 3 leaders and there is 1 follower, and all the read requests can be served by anyone, but the write requests, again like before, they can be handled by only the leaders, and then they can write to the followers. So yeah, of course, compared to the first model, which was leader follower, this model is better in the sense of it gets rid of the single point of failure, In case of leader follower architecture, we had just one leader, and that used to handle all the writes, and that was a single point of failure. If the leader goes down, then the system simply stops accepting writes until a new leader is elected. Whereas in case of multi-leader, even if one leader goes down, there are other leaders that are still available. But in case of cons, well, you can definitely see from here the conflict resolution can be difficult. Let's assume there is a same piece of data, same data row, let's say it is modified in multiple leaders simultaneously. So how do we resolve the conflict? Which write to accept? There are some complex algorithms to decide that. So we need to talk about that later. And finally, we need to talk about leaderless or peer-to-peer architecture. This is a case where all the replicas of the database can accept write requests. So everything can accept write, and of course everything can accept read as well. And of course, as you can imagine, the conflict resolution is even harder now, but some systems opt for the leaderless architecture regardless because of extremely high availability and scalability. One example is Amazon DynamoDB. When Amazon was implementing its checkout or shopping cart system or the order placement systems, they noticed that if the order placement system had any issues or any lags, then the customer would not really go through with the order, and that was hurting Amazon's business. So they had to go for some eventual consistency and complex rates and complex conflict resolutions in favor of fast response. So yeah, that's an example of leaderless. Let's now talk about synchronicity. So what do we mean by synchronicity? It is a type of replication that depends on how much synchronization happens with the data. So let's first talk about the synchronous replication. So write is committed only after all replicas acknowledge receipt. So let's say there are 3 replicas and there is a write request coming. So let's say this is the client and the write request is coming. So this is replicated to both the followers, and they will confirm their writes, and when they confirm their writes, finally the leader will confirm their write. So this is one way to replicate. So what are the pros here? Of course, strong consistency, because whatever data is there in the leader, they are also replicated in the followers, and we make sure of that. So there is no data loss on leader failure, because before the data being replicated, if the leader somehow goes down, well, we can maintain the atomicity in that case relatively easily, and we can just revert back the transaction. And the cons, of course, the higher write latency, the slowest follower, that will always be the limiting factor of our write speed in that case, and also reduced availability, because we have to replicate to all the followers. If one of the follower goes down, then we won't accept the write. So of course there is a lot of chance in this model to reject a write, so the system is not available for writes more often. What is it best for? So critical data where consistency is paramount. For example, we have financial transactions in banking sector or in stock market, where the data needs to be very consistent. It can't be that from one machine I see $1,000 of balance, and from another machine I see $1,100 of balance. So let's say there is a write which is plus $100 deposit, and all the databases has the record $1,000. So after $100, what should be the balance? It should be, of course, $1,100 everywhere, right? And because we make sure that the write is replicated everywhere, regardless of which copy of data we connect to, we will see $1,100 balance regardless. So yeah, that's a very big advantage of synchronous replication. Then we can talk about asynchronous replication. So in this case, it is something completely different, as you can imagine. So let's say I have a few replicas of database, I have a leader, I have 2 followers, and I have a client writing. And once the leader confirms the write, then I will see the write is accepted. Whereas the leader then asynchronously replicates the data to the followers. So in this case, there is no guarantee that eventually the followers will actually receive the writes. So of course, as you can imagine, the pros are lower write latency, because we don't have to wait till all the followers accept the write, unlike the synchronous replication, and that leads to higher availability as well, because even if the followers go down, we will still accept the write, so there is less chance of request failure. But the potential for data loss on leader failure is much higher. Let's say before replicating the data itself, the leader goes down. In that case, there is no guarantee that data would be saved anywhere, because the followers don't have that piece of data anymore. So if this leader does not come back up again, the data might be gone forever. So yeah, where is it most common? Widely used when some data loss is acceptable for performance or availability. And then there is the semi-synchronous replication, where as you can imagine, it's a mix of both. We have a leader, 2 followers in this example, and there is a client which sends the write request to the leader, and leader takes care of replicating the request, but leader, let's say, waits for only 1 follower to respond back, and if this one responds back, leader says okay. If anyone responds back, for that matter, leader says okay, the write is accepted, and it sends back the response. So of course you see the availability is more compared to asynchronous. The availability is less compared to asynchronous, but more compared to synchronous. Yeah, it's a best of both worlds really. It balances consistency and performance, and most of the databases actually use this kind of model, and most of them go by the strategy of the majority. So for example, if we have 3 nodes in this case, if 2 nodes accept the write, then we say okay, the write is accepted. If there are 7 nodes, then if 4 out of 7 accept the writes, we can say the write is accepted. Well, replication is definitely necessary for distributed systems, as we have seen, but it comes with its own challenges, of course. So first of all, we need to figure out what kind of consistency model we want to go for. If it is strong consistency where all reads say the latest write, then our consistency model or synchronicity model has to be different. Then the eventual consistency, the reads may see the some stale data, but replicas eventually converge. But for the sake of performance, we can sometimes choose this. So choosing the right model is a critical trade-off in CAP theorem. So what is CAP theorem? I'm planning to make another video on this, but let's quickly go over it. So CAP theorem basically says we can choose only 2 of these 3, which are CAP. What is C? C is for consistency, and A is for availability, and P is for partition tolerance. And when we are making a system partition tolerant, which is generally the case in case of distributed system because the network partition is pretty common, then we have to choose between C or A, which is consistency or availability. If we lean towards consistency, we have to sacrifice availability, and vice versa. Then the replication lag, the delay between write on the primary and its application on replicas, and can lead to stale reads. Then conflict resolution, of course we talked about it. It's a complicated problem to solve when there are multiple writes on multiple leaders on the same data. Then there can be network partitions, and due to network partitions there is split brain. This is a typical problem in case of replication. So let's say when network issues, they isolate the nodes, the leader and can go down. So there's let's say 1 leader and 2 followers. The leader goes down, so the raft algorithm or whatever leader election algorithm we use, we promote this one to a leader, but now this leader comes back up again due to some temporary issue and it recovered from that. So in that case, the whole system thinks there are two leaders, because this node thinks it's a leader, and this node never got the information that it got demoted from being a leader. It still thinks it's a leader. So there can be complicated issues because of that, and that's a split brain problem. And failover and recovery, of course, how to detect a primary node failure, elect a new one, ensure seamless transition for clients. So which replication strategy to choose? Again, it depends on the use case really. Do we need to prioritize high consistency? For example, is it a banking service or a financial service? Then lean towards synchronous and then leader follower topology. If it is some high availability scalability scenario, then explore asynchronous and multi-leader or leaderless topology. And of course, data durability, this is crucial for all. So make sure you have enough replicas of databases so that in case of a geo disaster or something like that, you can recover the data. So hopefully this has given you some idea about replication. So if you like my content, please like, share and subscribe. See you in the next one. Thank you.